This is my continuing discussion of derivatives, and we're going to start with something simple, and then we're going to go to something a little more complex. Like I've said in the last 4 videos that I've done about derivatives, we're trying to find instant speed. The speed that you're traveling at the moment of, say, an impact. Say when a bullet actually hits your body. Or when your car hits a deer, or when your car hits another car, so on and so forth. Knowing that speed at that very precise moment, and it's not even a second, because remember, if you measure things within 1/10 of a second, things can change dramatically within 1/10 of a second. Remember, in my previous videos, I said that something can change 16 feet a second. A ball can drop 16 feet in 1/10 of a second. Well, let me tell you something. That's quite a dramatic figure. I mean, to think that a ball can travel 16 feet in 1/10 of a second, that's a big deal. And it becomes an even bigger deal if you're talking about the moment that your car collides with another car, or your car collides with a deer, or if a bullet actually hits you in the chest. Somebody tosses a bullet at you, it's going to sting a little bit. It's not going to hurt. It's not going to be a permanent injury. Somebody shoots a bullet out of a .357 Magnum, that could be a permanent injury. That could be a permanent death injury. Okay. Now, how do we usually figure out, you see it all the time, you say, well, I have to travel 30 miles an hour in a certain part of town, but in another part of town I can travel 60 miles an hour. How do you even figure that out? Well, you're going to say there are 30 miles to cover. You're going to cover it in 1 hour. So if you divide 30 miles by 1 hour, you get an average rate of speed during that hour. So you're going to be traveling a certain amount of miles, or a certain number of feet per minute. And you can figure it down to per second, or per 1/10 of a second, or something like that. So 30 miles, which we're going to represent with the letter D, and an hour, which we're going to represent time here with the letter E. Divide the 30 miles with the hour, and you come up with a per minute ratio, so on and so forth. Okay? Now, in calculus, we use a lot of subscripts. Let's say we want to represent 6 seconds. Second number 1, second number 2, second number 3, second number 4, second number 5, second number 6. Okay. Or maybe we want to represent the distance traveled during a particular second. So, we have this equation here, S equals 16t squared. Now, in this equation, t represents time, S represents spatium, which is a distance, okay? So, the distance covered in the first second is S1. The distance covered in the second second is S2, so on and so forth. And over here is S6, which is the distance covered within the 6th second. Okay? Now, in the equation, if we plug in the number 5 into this equation, we square it, it becomes 25. We multiply it by 16, and it becomes 400, which means that we have traveled 400 feet in just 5 seconds. Okay. Now we're going to figure in a little bit more. We're trying to find an increment here. Okay? We don't know what that increment's going to be, so we're going to represent that increment with a letter. This is where variables come in. And I talked about variables in a previous video. Okay, so I talked about variables in a previous video, and now we're going to start applying them here. We want to represent a certain number of feet traveled beyond the 5th second. We've already said that a ball has dropped 400 feet in 5 seconds. Now we're going to say it's going to drop an additional amount of feet. Now we already showed that a ball can travel 16 feet in 1/10 of a second. But in this case, we don't know how many feet it's dropped, because we're going to have 2 new variables. One is going to represent the number of feet that the ball drops after the 5th second, and we're going to have another variable called e. Okay, so e is going to represent time after the 5th second. Okay, because remember, time always moves forward. Second number 5, second number 6, second number 7. So we're going to have E represent a time after the 5th second, and D representing a number of feet that the ball has dropped since that 5th second. Okay? So we're going to say S5, which represents the 400 feet that the ball has dropped for 5 whole seconds, plus the distance that the ball is going to drop after that 5th second, is equal to 16 times 5 plus E. Now, where do we get the 5? Well, we've already said that the ball has traveled for 5 full seconds. Now we're going to say that the ball has traveled for another number of seconds. We don't know how many seconds it has dropped. We don't even know if it's just even a tenth of a second that it's dropped, but it has been longer than 5 seconds. It could be 5.1 seconds, 5.2 seconds. It could be 5.01 seconds. But this E represents the time since that 5th second. So we've factored this equation out here. And as you can see, 5 plus E times 5 plus E comes up to 25 plus 10E plus E squared. And we did this through factoring, which was in a previous video. And if you don't know what we're talking about, you need to go back to that video and watch it and come back here. So now, 5 plus E times 5 plus E gives us 25 plus 10E plus E squared, and we're going to multiply it by 16 because we have replaced the T here with 5 plus E. Alright, once we multiply 16 times each one of these terms here, we get 400 plus 160E plus E squared. Now, we've already said that S5 represents 400 feet. This is where we get the 400 right here. Alright? Now, we're going to subtract 400 feet from this equation. We're going to subtract it from both sides of this equation, so that S5 is going to disappear and that 400 is going to disappear, leaving us with distance equaling 160E plus E squared. Now, remember when we said when you have 30 miles an hour, you're going to divide that 30 miles by an hour, okay? We don't know how many feet has dropped since the 5th second. We also don't know how much time has elapsed since the 5th second. So we're going to divide both sides of this equation by the number of seconds that have passed since the 5th second. That's where we get the D over E. And when we get done here, we have D over E equaling 160 plus E squared. Okay? Now, even though we don't know how much time has elapsed, we know the average speed that we need to know for the point of impact, which is 160. That's our instantaneous speed right there, is 160. We got that through this whole equation. So we have actually derived from our original equation right here, S equals 16t squared, the number 160, which is what we are going to call our instantaneous speed. And that's how we derived it. You may want to play this video over and over again until you get the concept of what we're trying to do here. But as you can plainly see, it is not that difficult to get instantaneous speed from a particular equation. And I'm going to stop it right here because I want to go into further discussion, and it's going to be taking too long for this video. So stay tuned. Derivative coverage is not yet over.